Footsteps of Vitruvius, design and construction durability lessons learned from the hands-on study of 2,000-year-old historic construction with Matthew Bronski. It is our hope with these lectures going forward will be free to paid members of the ICAA. So please consider joining our organization if you're not already a member. If you are a member and from another regional chapter, please send our executive director, Sarah McDonald, your email address, and you can be added to our regional mailing list in addition to your own. Sarah will also post her contact information as the presentation begins. Please note, participation in this lecture includes AI credits. Sarah will also post a lecture of that again as soon as the introduction ends. Please save your questions for the speaker until the end, and then we'll post them in the Q&A window, which opens with a button at the bottom of your screen. But that being said, we have almost 150 people signed up for this lecture, so please open up the chat window, introduce yourself. Let us know where you're all from. For those of you that are new to the ICA, we're a leading nonprofit organization dedicated to advancing the classical tradition in architecture, urbanism, and the allied arts. We do this through education, publication, and advocacy. The Institute, our mothership, is located in New York City with 16 chapters across the United States. Nationally, the ICAA offers a broad range of educational programs, including intensives for architecture and design students, introduction programs for middle school students, lectures and walking tours for the public, continuing education courses for professionals and enthusiasts, travel programs to visit classical masterpieces, the publication of original and reprinted books, and an annual journal entitled The Classicist. Regionally, in addition to providing the education and tours that I just mentioned, our New England chapter hosts our Bullfinch Awards annually. This year, just recently, October 2nd at the Harvard Club in Boston. It's there that New England celebrates its best accomplishments in traditional and classical architecture, landscape architecture, interior design, and the allied arts. Again, please consider joining our family. In this lecture, Matthew Bronski, the 2009-2010 recipient of the National Endowment for the Arts Rome Prize in Historic Preservation and Conservation, will present some key findings from his Rome Prize research. His 10-month-long Rome research project was comprised of hands-on study of approximately 24 historic buildings in Italy, ranging from 1st century BC to early 20th century BC, including buildings by Bernini, Borromini, Moretti, and others. His hands-on research, often on scaffolds of buildings under restoration, diagnosed successes and failures in durability of construction detailing to derive lessons and general principles for designing buildings more durably and hence more sustainably today. For the past 25 years, Matthew's practice at Simpson, Grumpert's, and Hagar, Inc. in Boston has focused on investigating and diagnosing causes and consequences of building envelope and structural problems in historic buildings and designing sensitive and appropriate repairs and restorations to solve those problems. Matthew holds a BS in civil engineering from Tulane University, a master's from the University of Pennsylvania, and an MS in historic preservation from the University of Pennsylvania. He's a fellow of the American Academy of Rome, recognized professional of the Association for Preservation Technology International. Matthew has led several envelope investigations and historic design efforts on numerous historically significant buildings over the years, including National Historic Monuments. They included the exterior renovations of the Lowell House, 1929, and the Harvard Hall, 1760 at Harvard University, the Boston Athenaeum, 1849, and H. Richardson's Trinity Church in Boston, 1877. At SGH in-house laboratory, he has supervised an analysis and testing of historical building materials, including mortar, brick, sandstone, granite, marble, clay tile, and historic glass. He has written and lectured on extensive topics ranging from preservation philosophy to facade inspections of masonry to traditional slate, clay tile, and copper roofing. This is Matthew's third such presentation for me in 8 years for both the AIA and the ICAA. Please welcome Matthew Bronski.
Thank you so much, David, and thank you everyone for joining us today. It's really a pleasure to be here with you. Let me just pull that up. Just want to check that everyone can see that screen. So David covered the lecture title, and as he mentioned, this really comes out of an independent research project I did for a year in Rome about a dozen years ago now. And yay, legalese. And really what I want you to get out of this is just understanding how important it is to really look back at historic construction. And it is so relevant today towards understanding how to design durably today, both with new buildings and for renovating existing buildings. So an outline of what I'll cover today, a little bit of an introduction, and then I'll introduce the concept of architectural Darwinism. I'll do a few exegeses or detailed breakdowns of a couple specific construction details to understand how and why they're durable. And then from those, I will extract some general principles of durability. And then I'll wrap up with a little closing and we'll get into our questions and answers. So just a little opening food for thought to get the wheels turning. Here are two basic schematic diagrams. A step pyramid, or kind of a wedding cake, you might call it, on the bottom, and an upside down or inverted step pyramid on the top. Which of these two do you think is the more logical, durable way to build? What does your intuition tell you? And I think intuition actually counts for quite a bit. And then which answer would a study of historic precedent suggest? Or more simply put, if you were to look back through the history of architecture, buildings in different countries and region, which of these two do you think you'd see more of? So we're just going to let that steep, let that marinate, and we'll come back to that later. So Vitruvius was in my project title and was really the inspiration for my year-long research project on durability in Rome. And I know this crowd knows Vitruvius really well and doesn't need an introduction, but just as a bit of review, this was Marcus Vitruvius Pollio. He was born and died in the 1st century BC. And we think of him today as a Roman architect, and of course he was, but it's important to remember that the hat that the architect wore in ancient Roman times was really quite broad by today's definition. So the Roman architect encompassed all the disciplines that we think of today as architecture, engineering in its many forms: structural, mechanical, environmental, military. It also included urban planner, master builder. So there was really quite a lot to being an architect 2,000 years ago. And of course, he famously wrote De Architectura on architecture around 25 BC. And we know it very well, often called the 10 books today, although it was one book essentially with 10 chapters. And we know it so well because it's the only surviving architectural treatise from classical antiquity, either Greek or Roman. But we know there were many others, and he actually describes them to us. And he tells us that he pulled the best from each of those works. So I think if one were to survive, it was really perhaps the best one, since he does kind of survey and read and cover and include highlights of all the others in his work. So my project in Rome wasn't a study of Vitruvius per se, or his treatise, or his built work. And it was not a study per se of how Roman buildings were constructed, but looking at those were really means toward the end. So I was inspired by the methodology of Vitruvius, and in particular, Book 2. And so what he did and described in Book 2, if you can remember from way back when, reading this in college, was he studied construction that either proved durable or not durable. And he really put on his detective hat to diagnose why. And from those lessons that he figured out, he developed and he published in the manner of the day, scrolls presented to the emperor, lessons learned for building more durably moving forward. lessons for future generations. So I found this really inspiring. So what I tried to do in my research project was basically use the same approach that Vitruvius did and pick up where he left off in time. So his work and his treatise concluded in the 1st century BC. That's where mine began. And I picked up where he left off in time and looked at buildings from classical antiquity all the way through kind of, medieval, Renaissance, Baroque, early modern buildings, even early 20th century icons, looking at them closely, diagnosing why they had proven durable or not. So I think I'm here in Boston and here in New England, where this chapter is based. I think we're pretty fortunate in that it has such a rich architectural history for the US. So we're looking back at buildings that are 200 some odd years old in a lot of cases. But of course, Rome is a whole different order of magnitude and timeline in terms of building history. So you're talking a tenfold increase in buildings that span 2,000 years roughly rather than 200 years. And also a different climate and a different tradition of construction and different predominant materials meant it was, it was a great opportunity to test some of the theories I'd developed after practicing for 15 or 20 years to see how they hold up in a different climate and a different tradition of building. And for those who know the Academy, I think my research project to a lot of my fellows that I was there with was a little bit unusual, where I was up, I had a hard hat and I was up on the scaffold and I was measuring things. And, a lot of them would go to libraries and research manuscripts and things for hours and hours and hours. And so it was just so different than what they were doing. They were kind of fascinated with this. But I pointed out to them that you look at the old photos of the AAR fellows at the Academy, and there's one from the Academy archives on the right. And they were really doing what I was doing. They were climbing up on ladders and scaffold, and they were measuring moldings. And so to me, it was kind of a back to the future type of project. So my work in the US for Simpson, Gumpertz, and Hager for the past 26 years has involved a lot of diagnosis of what has gone wrong with this building. And sometimes it's a 100-year-old building that's done pretty well and it just has a few problems. And sometimes it's a brand new building that has a lot of problems and it's a big lawsuit. But in either case, I often have the opportunity to use a lot of fancy test equipment and non-destructive test equipment and to make a lot of sample openings with the help of contractors, as you see on the lower left photo. So that methodology on my project in Rome really wasn't possible. I couldn't bring all that equipment over there for a whole year and keep it away from my colleagues at work, and I wasn't about to ask permission, and I certainly would not have received permission to make openings in 2,000-year-old buildings. So how was I going to do this project? So really, the methodology was like Vitruvius. It was kind of back to basics. It was a lot of looking really closely, just looking, drawing, thinking, looking, drawing, thinking. How does this work? Why did that fail? How did this hold up and stand the test of time? So one of my partners who kind of teaches a lot of us how to use some of the non-destructive testing equipment at SGH, some very sophisticated, inexpensive gizmos, likes to remind us that the two best tools you have on any investigation, you always have with you, and they're your own two eyes. Just looking very closely, thinking about something is just incredibly valuable. So I think there was really a need for this, and still is a need for this research on durability. So in preservation, and part of my background is in preservation, I think there's a lot of research at the micro scale. So the kind of tiny scale of microscopes and looking at materials, up really close and understanding the slight differences in chemistry and all of that. And there's a lot at the macro scale. What are the character defining features of this building or even this whole district? And there's not enough at the intermediate scale. And by the intermediate scale, I mean the scale of a window, the scale of a corbel, the scale of a bracket, the elements that you actually, how you put a building together, how wall meets window, how roof meets wall. That intermediate scale is really critical. And in my experience, that's where buildings really either do well or fail in terms of their durability, is at that intermediate scale. So just to kind of make that point, here are a handful of different window details. And at a glance, it just wouldn't be totally obvious to you why, half of these succeeded, roughly half, and why roughly half of these failed miserably. So it's important to just look really closely and get into the nitty-gritty details of how you bring different materials together, how things lap, how things get integrated, how things meet with respect to the weather. And another reason I felt this was really important is I see us in the midst of a durability crisis in architecture and construction, architecture, engineering, and design and construction. So there's really a pandemic of enclosure failures that I see from kind of the high-end, very expensive projects to the low end, from really renowned to unknown architects, from coast to coast. And many are failing immediately or very shortly after their construction. So anything from kind of these, McMansions and spec-builder eaves houses that you see here on the right from the southeastern US. This is a regional hospital in Ohio that I was investigating that was leaking badly and had a lot of problems even before they were done punch listing it, to the very high end, famous architects, significant commissions and talented teams of consultants too. So it's not my point to blame these, it's just to say this is such a widespread problem that is spanning the entire gamut of big projects to small and everything in between, coast to coast. And yet another reason I felt this research on durability was really important is there's been so much focus, and rightly so, on sustainability over the last 25 years. And in my mind, durability is absolutely fundamental to sustainability. So we can't really talk about designing and building sustainably if we're not talking about designing and building buildings to last 100, 200, 300 years. So if you look at a building that's a couple hundred years old, like Palazzo Bronski at the upper right, or that's maybe around 500 years old, like the Villa Medici at the lower left, think of all the embodied energy material that has been saved and not knocking down a building every 50 years for 200 or 500 years and starting all over again and quarrying or manufacturing new materials and transporting them to the site and erecting them. Think of how much you're saving. So one really good study that looks at just this, looks at sustainability from the broader lens of the total impact on the planet of knocking down a building and building a super energy efficient building, replacing it with that, versus making some improvements, not getting it to the greatest performance energy-wise, but keeping what you have. Kind of the greenest building is the one that's already built notion. Is this greenest building study that you can download? It's if you Google the greenest building, National Trust, or Preservation Green Lab, you'll find free downloads of this very good study as a PDF. And they found that in over 90% of the cases, looking at different cities, different climates around the US and different building types, it's really best for the planet to save and rehabilitate that building rather than knock it down and build something that's even much more energy efficient than you could get with an existing building with modifications. So clearly we have this crisis in durability, but why? It's despite the decades-long emphasis on sustainability. So I see several reasons for this. One is that aesthetic innovation, kind of the constant push for aesthetic innovation in architecture, forces us to innovate in our detailing. So we want something to look a different way. We have a new material, we have a new membrane, we have a new frame element or whatever coming out, and we have to figure out how to detail that for the first time. And it's possible, but it's certainly not easy to get it right when you're detailing something for the first time. You're just starting to get to know a material or component, or how to bring a couple different unknown materials or components together. So that's understandable, but I think we're forgetting some fundamentals and some first principles and real basics of designing for durability. So that's really what I'm going to try to cover today. So another kind of surprising thing that in my work over the past quarter century at SGH, I've worked on a lot of traditional, older picture postcard historic buildings like you see on the right, the old State House in Boston or Harvard Hall or Lowell House, as David mentioned. And in the past 10 years or so, I've really worked on a lot of significant modernist buildings, like the Holyoke Center, now known as the Smith Campus Center, the Philip Johnson Thesis House, the Gropius House. And in that work, I've really seen more and more significant original design problems on the modern contemporary envelopes than I have on the traditional buildings. So why is that? Well, in my mind, this comes back to this concept of architectural Darwinism. And so I've used that term to describe this kind of process. So this process is a highly evolved architectural or structural form, like a Northern French Gothic cathedral, you see Beauvais here, does not tend to arise instantaneously. It's not this genius lightning bolt idea, that comes out of the sky straight into the hand and through the pen and onto the paper. That's not really how highly evolved architectural or structural forms happen. What tends to happen, how you tend to get a highly evolved form, is more like a gradual evolution and a series of baby steps that it eventually culminates in that. So we don't just go straight from kind of squat medieval structures to Beauvais Cathedral. There are some early Norman buildings that are starting to open up, starting to get less solid, less massive, get a little bigger. They come up with the pointed arch as opposed to the Roman arch. And then if you look at cross sections through Northern French Gothic cathedrals chronologically, and I've arranged these chronologically from upper left to lower right, you can see the evolution where they're getting taller, thinner, and more slender. And it's really hard to build a tall, thin, slender, unreinforced masonry structure, and these are unreinforced masonry, on a really large scale. So you can see this kind of progression that eventually leads to Amiens over the course of more than a century. And that doesn't happen without some bumps in the road, kind of figuring things out along the way. So Beauvais Cathedral alone had 5 collapses that are documented that occurred during the construction. So there's some trial and error. People make some mistakes, they figure things out, and they eventually get it right. And they don't always get it right. Some things are failures. So over time, only the best survive intact. So when you look at a highly intact historic or ancient building today, like the Pantheon in Rome, or structure like Pont de Gare near Nîmes, France, those are, it's survival of the fittest. So those are among the best that have just withstood the time and the elements for 2,000 years and are just remarkably intact. They were so well designed and built. So if a building was poorly built, it would wind up in ruins. And it's important to remember that not everything that winds up in ruins was poorly designed, because many buildings in Rome that were really well designed wound up in ruins just because, they became quarries essentially for later generations to pull stones from, to pull materials from. So I would document this I would diagram this process of architectural Darwinism like this, with time moving from left to right. So you have either a new material or a new form or a new method of building that's tried out. There's some trial and error. There are partial or even wholesale failures. People learn from those failures, both their own and for other people that are trying to do the same thing, like in northern France when people are building the Gothic cathedrals. And then time passes. Well, some viable techniques and details evolve and become known. And then time passes and time weeds out the lesser of those buildings, and the better of those survive, the survival of the fittest. So we come along 2,000 years later to work on Maison Carrée or the Pantheon, and it's a really fundamentally sound design. So our typical preservation approaches, like less is more and really don't change anything, do as little as possible, etc. Technically, those work pretty well because those buildings are so inherently well built and well designed. So just to kind of overlay on this, well, what happens with modernism? So we come along with, again, new materials, new forms, new methods of building in the early 20th century. And that same trial and error occurs, and people, again, don't get it all right the first time. But there isn't enough time to really learn all the lessons from those and digest them and assimilate them into our design and construction culture before we're moving on to the next thing and someone else is innovating with something else. So essentially, this whole process gets short-circuited and collapsed. So coming in and trying to preserve an early 20th century modern icon, in my mind, is much more difficult because there are so many more things that are inherent design flaws that have led to a lot of problems over time that need to be corrected or rethought. So just to kind of give an example of that, this farm at the upper photo, this is in Winchester, Mass, where I'm sitting right now. This is the little town about 8 miles north of Boston, where I live. So that's the Right Lock Farm, and a squash house on the left from about 1920, and a barn on the right from about 1820. So there was no architect. These were essentially built by farmers and local builders. So as an example of that, the accumulated knowledge with which a farmer might build these buildings, I have on the left a plate from Good Practice in Construction from 1923, about the time the squash house on the left was built. And so what you see there, clapboard siding, punched windows, double hung, doghouse dormers, etc. That was really well thought out and understood by 1920. We had that down pat by the 1920s in New England. And this plate of details is just fantastic. I wouldn't hesitate to build a house for myself today with these exact details. They're really well thought out from the standpoint of durability. So that body of knowledge was here. This is how you build a wood-framed clapboard house in New England in the early 20th century. So Walter Gropius comes over from Germany, has a new job at Harvard. He wants to build himself a house, and he's actually very inspired by these types of vernacular farm buildings in New England. They're very austere, they're very unornamented, they're very honest, and he likes that. So it relates to his modern ideas. So he picks up on that, and you can see even he's got the white siding, he's got the wood siding, he's got the same kind of color on the window scheme as the farm here. But of course, he gives it his own twist. So instead of horizontal clapboard, which all shingles to the weather, he puts the wood siding vertically and runs vertical siding. Instead of punch windows, he has horizontal strip windows. Instead of wood double hung windows, he has rolled steel casements. And instead of a sloped simple gable roof, he has a flat roof. So he's giving everything his own twist here. He's inspired by the aesthetic, but he's come up with he's inspired by the spirit of it, but he's reinterpreted it, and he's forced to invent all his own details to kind of pull off the look, the austerity, the kind of shadow lines, and everything else that he wants. So he has to invent his own window details, and that's what you see on the right. So this, long story short, was one of the failures, and when we went back to restore that building in the 1990s, and it was only 60 years old at that time, which is not old for a wood frame building in New England. It was really in pretty tough shape as a result of bad window detailing and a lot of leakage. So that's the concept of architectural Darwinism, and that's what makes it so difficult. So I'm going to take a couple specific construction details that I studied in Rome. I studied many more, but we just don't have time to share them all. So I picked two for tonight, and I'll break those down and understand why those traditional details that evolved over time and became very well known to builders and to architects work so well. So the two that I'm going to share with you tonight are these common facade forms that you see on the left and typical roof eave detail that you see on the right. And one of the reasons I picked both these details is they're just so omnipresent across so many different centuries. So, you can look at buildings from that are 500 years old, 200 years old, 100 years old, even less, and see these types of details that you see on the left, kind of projecting band courses, window heads, sills, all this articulation of the facade, despite changes in other stylistic, motifs during that time. And the same thing with this roof-to-wall detail. You'll see buildings spanning 2,000 years that have a detail very similar to this. So I think it's often a hint when you see something that's done across a period of time and it transcends many different styles, that there's usually a good reason they're doing it that way. So let's take a closer look. First, the facade form. So again, look at the shadows on the right. You see that every floor line, you've got that strong ledge or band course. You've got these big window hoods that project out, the big sills, a big overhanging cornice. Why do so many different buildings in different architectural styles from different centuries have these same features. Are they decorative or are they functional in some way? So in brown is my section of one of the buildings I was studying. That was actually Palazzo Bronski. So if these are all decorative or ornamental, then you could come along as a modernist and say, we don't need all that frippery. It's just, frilly nonsense. It's not really doing anything. Why don't we just clean it up and do something simple like this? So on the right, there's my conjectural section, taking Palazzo Bronski and kind of creating a modern facade. What would a modern facade of that same height and proportions look like? So that roof overhang goes away and you have a parapet, all those ledges and band courses at the floor lines go away, the sill and window hood projections go away. So if all that goes away, if they're purely ornamental, there would be no technical consequence for doing this, right? It would just be aesthetic. But my point is they really are doing something for a living, and here's how and why they work. So if you think about, these are mass masonry walls. They're load-bearing walls, so they're very thick brick or stone walls, and the floors all frame into them, and they carry the weight of the floors on down to the ground. So they're very thick masonry, but a lot of these buildings in Rome, these are 60 or 70 feet high pretty routinely. So if you look at my schematic diagram on the right, if you have a very thick masonry wall, it's raining, the rain is hitting the entire facade. If you could draw a cross-section through and kind of tint the water, this is what it would look like, and this is what happens. So when the water starts to flow down that facade, the masonry, even if it's perfectly pointed, is very absorptive. The mortar itself is absorptive. Brick is absorptive. A lot of stone, but not all stone is highly absorptive. So the water works its way in. There are two forces acting on it. Gravity is pulling it down, and absorption, capillary action, is pulling it in. So the result of those two forces, one down and one in, is that diagonal gradient. So what really happens with these walls is that's the gradient you get of wetting. So it's worse the farther down you go on the building, and you get to some point after it's rained a certain amount of time, and that water comes through at the inside, either in the form of free water leakage or in the form of moisture that just blisters your plaster, peels your paint, causes other moisture-related problems like that. So, how do you make this work? How do all these buildings that are 60, 70 feet high in Rome, how do they work? Because it rains there a lot. Well, this is really how they work. So those kind of ledges and band courses that you see at floor lines, those are really acting essentially like a through-wall flashing. So just structurally, to make those out of stone, you have to set those into the wall. They have to be cantilevered into the wall. And with just a slight wash slope on those stones, they essentially act like a flashing and get that water out. So they're essentially like resetting the clock at every floor line, so you don't get to that point, as you see below, where the water works its way all the way through. You get individual triangles at every floor of wetting rather than one big kind of soak through, as I've shown on the right. So they really are functional. So here's a medieval building, essentially a fortification from the 10th to 12th century, where they did not have any of these features. You can see this building isn't 60 or 70 feet high. It's more like 25 or 30. But without any of these features, that inside corner, this is the same corner I'm showing on the exterior on the right and on the interior on the left, you can see all the moisture-related damage there without having any of those features on the inside. So even very thick walls without these features are not immune to leakage and moisture-related damage. And this is going back 2,000 years now. So at Ercolano Scavi, a town that was like the more famous Pompeii, was buried by the eruption of Mount Vesuvius. I love going to Ercolano because you can see some incredibly intact construction details and buildings, even beyond what you can see in Pompeii. So this kind of pent roof that I'm showing here on the right and a close-up on the left, you can see that the clay tile are actually built into the stone wall on just this little roof, pent roof is called, a very short roof that just projects out a foot or two. And so why would you go to the trouble of building that all the way into the wall? So you can see there's a section I've drawn at the upper right that, that's much more of a pain to build. any builder would say, why don't I just build the wall straight up, and then you can come along later and just nail a wood ledger on there, then hang your little roof on it or whatever. I mean, that would be a lot easier to do sequence-wise. But they took the time, they took the trouble to build the wall up and then stop and then build this in and build these clay tile into the wall, deep into the wall, and then continue on up. So this is, again, essentially functioning like a flashing. It's catching water, as you see in my little diagram at the upper left, that's getting into the wall, catching it, and then bringing it back out again. So just the notion that they would go to the trouble during construction, take the extra time to build it this way, tells me that they really understood how this worked and why this was important. The second detail I'd like to break down for you is that omnipresent roof eave detail seen really across 2,000 years of buildings in Rome and the central Italian peninsula. And there's my drawing of it at the right. So that particular drawing I did of it was actually from the Casa di Dante in Rome. So that's a late medieval building in the Trastevere neighborhood. You see it at the lower left there. And just to kind of show you what this is, so the main element that's kind of got the scrolly cut sticking out of the wall, that would be usually a blocking member underneath the attic roof truss or underneath the main floor beams in the attic or top level. That's about at 10 feet on center. You can see those kind of poking out on the facade on the photo at the left. There's a continuous rail that spans between those, and then you have rafters that land on those at about a foot on center. So it's a beautiful detail. It's, a lot of people think it's ornamental. So is it just ornamental, or is that, functional in some way? Sorry, slides are skipping ahead a little bit here. Let's get back. So obviously, it serves a broad function within the building. The roof overhanging the wall, you want to clear the water from the roof. In Rome, they typically did not have gutters for many, many centuries, and even today, a lot of buildings don't have gutters. So that roof runoff, you want to clear it from the wall. And in particular, that's important where you have building materials like the one I've drawn at the left, which is 2 foot. So you have a stone that's not very durable at all. That's the same as the center photo, the Casa di Salone, and to clear that water away from the wall to make the wall more durable. So there's an overall function here of this making the wall more durable. And you can see on the photo at the right, this is a small little school that I walk by every day that even a relatively modest overhang for Rome, this is modest, it's about 1.5 feet or so. A lot of Roman roof overhangs are about 3 feet. You can see the line of erosion in the pavement showing you that when you don't have a severe wind-driven rain, most of the time this is clearing water effectively to the ground and keeping it off the facade. And as I mentioned, many roof overhangs in Rome are much, much more generous. You see an example of that on a medieval building at the upper right. So this kind of corbel cut beam end or wood end, so that cut is really not decorative. And again, you see that from the 1st century AD down below all the way up to the McKim-Eden White building I was in from 1912 had a very similar detail to this. So spanning 2,000 years. So here's how it really works. Cutting that beam off, you might think, why don't they just cut it straight off? Why do they have to do that decorative detail? Well, in terms of structural form finding, you have a cantilever with a point load at the end. So the form that wants to be structurally is really the moment diagram, which is that triangle. So they've cut it off and they've left exactly the shape that they need, the form that they need structurally. And you might think, well, why not just leave it? Well, the thing is, if you leave it, you have end grain exposed to the weather. The end grain wicks the moisture in through capillary action. And when they do leave it, and I've seen on houses here in the US, beams that were cut off straight without a gutter, this is exactly how it rots. Again, it's the same gradient. Gravity pulls it down, capillary action pulls it in. The resulting gradient is triangular, and the lower half rots. So there's actually a beautiful synergy here where the part you want to cut off the cancer before it spreads is the part that you don't need structurally. So you really do want to cut that off. And that leaves you with exactly the form you need structurally. So then you might say, well, why not just do a simple diagonal cut? Why do you need all those little curls and turns? And the thing is, if you look at the photo, or my watercolor sketch in the middle, the roof overhang is really shielding this from the weather pretty well. So even in a 45-degree wind-driven rain, you wouldn't be getting water on that wood member. But in a horizontal wind-driven rain, when that does occasionally get wet, what you really want to do is get the water off it as quickly as possible. So essentially, these cuts that might look ornamental really build in a whole series of drip edges so that when it does get wet, it drips and it dries very quickly. And the thing that first got me looking at these details and kind of sketching them and drawing them again and again and thinking about them was I was just blown away that you would have 500-year-old buildings, medieval buildings, that had wood exposed to the weather in Rome, a rainy climate, it really rains all winter, for 500 years, and they would still be intact. So obviously these weren't pressure treated. They're not painted. They're just dark because they're so old, they're heavily oxidized, and they're not cypress or teak or mahogany or naturally decay-resistant wood. They're usually pine and occasionally chestnut. So how do you keep a non-decay-resistant wood in a rainy climate alive in the exterior for 200, 300, 500 years? So it's really the way this is configured and detailed that leads to its success. And even kind of the tiniest dimensions, like how far does the clay tile overhang that wood rail at the very end? This is a very rustic example from the courtyard of the Palazzetto on the left. But one of the first buildings I was up on, the roofing foreman told me that overhang, how far do you overhang it? And he said, this has to be about 7 centimeters, which is about 2 3/4 inches. And what he explained to me is if that dimension's too short, what happens is all the water curls around the clay tile and it comes back and wets the wood and the wood rots. And if that overhang is too long, then someone puts a ladder up to it or someone steps on it and it breaks off. So the just right, the kind of Goldilocks dimension is about 7 centimeters, which is about 2 3/4 inches. And there's the foreman, Camone, who explained this to me during his re-roofing project. And sure enough, that was one of the first buildings I got up on all year through the kindness of RISD. Thank you, David. Let me up onto that building where they have their architecture studios in Rome. And every other building I measured as soon as I got up there, that clay tile roof overhang, including much older buildings, much newer buildings, buildings by Borromini, and right on every time it was right around 2 3/4. Everyone had that perfect dimension. So taking just a second here, I'll now pan out. So kind of looking at these and many, many more individual details like these in Rome, at the end, I kind of extrapolated out, what are some general principles of designing for durability that I can derive from all these individual lessons. So that's what I'd like to share with you now. So here they all are, but I'm going to first come back to that original question. So which of these is the more logical, durable way to build? Is it the inverted step pyramid, upside down? And please feel free to throw your thoughts in the chat. Or is it the kind of step period or wedding cake on the bottom? And as to what your intuition might tell you, your intuition kind of represented by these children's blocks might say, well, Julie, it seems a lot more durable or maybe more structurally stable to do the step pyramid. And if you were trying to think of my question of, which of these would you see more examples of if you look back through the history of architecture? I mean, maybe you thought of a step Mayan pyramid. It might be hard to think of examples offhand of the inverted step pyramid. So really, the answer is the inverted step pyramid is the more logical, durable way to build. And so to explain why, I'll show you these diagrams. So if you think about designing for durability is really all about managing water. It's one of the most essential things no matter what climate you're in. If you're in Rome, if you're in the cold northern states of the US, where they have significant freeze thaw, if you're in the Mediterranean or California where they don't, water is still the foremost agent of deterioration. So designing for durability is all about managing for water. So the step pyramid is structurally very stable, but the downside is how it manages water. So if you think about a 45-degree wind-driven rain on our wedding cake, every surface of that, every transition, vertical to horizontal, is just getting pounded by the rain. And every place you've got to have kind of a perfect watertight assembly to keep that all dry. It's very challenging to detail. One building that had that form that I spent a lot of time dealing with leakage on and correcting leakage problems shortly after it was built is shown at the left. That's the Thousand Arts Civic Arts Plaza in just outside Los Angeles. And that was an early 90s building. So if you think about the inverted step pyramid, Boston City Hall might be one example that springs to mind if you're here in the New England area. And maybe it's hard to think of others, but the way this really works well in terms of water management is you're shedding and sheltering. So by shedding, I mean you're dumping water not just down to the next floor on the facade, but you're clearing it all the way to the ground. So at each of those overhangs at every floor level, you're clearing water right down to the ground, just like our Roman roof example did. And you're also sheltering. So even in that 45-degree wind-driven rain, those areas I've shaded with red never even get wet. So it's much less torturous on the waterproofing installation or the materials than the step pyramid design. So Boston City Hall, okay, there's one example, but do you really see examples of the inverted step pyramid in older architecture? So here a couple blocks away is the Paul Revere House, just the second oldest building in Boston, 1680 to 83. And it's more subtle than my diagram, but there it is. If you look closely, you'll see that overhang at every floor level, including the attic level, and even a little jog out at the foundation there. So it's definitely there. And now that I've seen it, I walk around and look at older traditional buildings of many different periods, styles, times, and I see it again and again. So kind of this early 20th century Tudor revival on the left, kind of a Queen Anne in the middle from the late 1800s, a Greek revival on the right from like 1840 or 50. They often have this general enclosure form. If you look closely enough, you'll see it. So it's, again, it works really well by shielding and sheltering. And a lot of it goes back, you look at the Tudor revival example here, and you'll see this again and again on older Tudor Elizabethan cottages in England, but also older buildings in the Alps in Bohemia have this type of form. And I think there's a myth that, you see this because people were just living all on top of each other in the Middle Ages, and they were trying to eke out just a little bit more space to live in dense, crowded cities. And, this 15th century cottage in Sussex, England, photo from my friend John Fiddler, that was built in the middle of a meadow, and it had these. And you see this in very rural buildings as well. It's not confined to the city. So to me, that kind of busts the myth that this was just to gain a little bit of extra floor space. I think they really knew what they were doing, and it was about water management. And so when you take, again, materials like untreated wood that's not naturally decay resistant, wattle and daub, which, you get that wet for very long and it just falls apart. It's essentially wicker with clay or lime-based plaster in it, as you see in the second photo from the left. You get that wet for very long and it turns to oatmeal. So you need an overall enclosure strategy and form that can help give that a chance to succeed. And that's what the inverted step pyramid does in all those climates and all those regions. In England, in the Alps, in Bohemia, you will see it again and again. And even in Venice, there are some really great examples. So, here they have masonry buildings, some of which are even corbelled out on timber framing, as you see in that second from the left photo, to kind of create that overall building form. So there are other ways to shed and shelter and other variations on this theme. So the Pantheon, if you look at the kind of measured architectural and archaeological drawings of it, the wall is planar, but the band courses at the different levels, even though they're chipped away and eroded, the reconstruction drawings all clearly show that they actually step out a little farther as you move up the building with height as of schematically diagrammed on the right. So I think here even, is that same idea that you want to shed water all the way to the ground and not just dump the problem on the floor below, not just kind of kick the can down the road. And yet another variation on this theme, the Basilica Palladiana, Palladio's Basilica in Vicenza. So here, the walls are planar, those kind of copper-clad ledges are planar, and then these, what the Italians call docione, which is like a big shower, it's almost like that big copper scupper. You can see these project out farther at the higher levels than at the lower levels, again, with the idea to clear that water all the way to the ground. So several variations on the theme, different ways to get there, but all with the same kind of overall goal of water management. So shed and shelter. And if you look at many other details, such as window hoods, those ledges, those band courses, the roofs overhanging the walls, I mean, these are all details that are about managing water, shedding, sheltering, protecting the most vulnerable areas, protecting materials that are less durable in their own right, like wattle and daub, like stucco on soft brick, like soft stones like tufa, etc. So all about water management. The next principle is, so the first one is, in summary, water management is paramount. Do everything you can to manage water. The second is put each material in a position to succeed. And what I really mean by that is not everyone can afford, and not every project and not every budget can afford the best materials everywhere all the time. So you really have to think about allocating your budget, allocating what budget you have towards putting the right materials in the right places. So I thought a great example of this was just this whole little town of Ercolano that was buried by the eruption of Vesuvius. And again, you can visit this town today as an excavated archaeological site. And so in this town, they had three really common stones in this area. They had basalt, this black stone that's just highly durable, really, really durable. They had tufo rossidus, which is kind of moderate, pretty good durability. And then they had this tufo giallo, this yellow tufo that you see at the upper right that is just non-durable, really falls apart without being exposed to the weather for very long. So you look at this wall on the left, you look at this photo at the upper right, and it almost looks like kind of a picture postcard photo from a preservation textbook about the harm that a really hard mortar can do to historic masonry. But that's the original Roman mortar. And what you really see there is, the stone is so soft, it is just eroded faster than the mortar even. So it's just not a durable stone at all. But what they did was they put each stone in the right place. So the beautiful, hard, shiny black basalt, they didn't use it in just ornamental places like countertops. They actually used this to pave the streets because that is the most severe environment. It's sitting there in water all the time. It's on a horizontal. You've got, animals and carts rolling over it, et cetera. It's getting pounded. That's where you use the best material. The second best material, the tufo rossidus, they're using on the curbstones. So they're up a little bit out of that. They haven't got the wheels and the hoofed feet of the animals on them all the time. So that's the pretty good durable material. Then the least durable material, that's what they're actually building the walls of all these houses and all these little shops out of, that yellow stone, again, you see on the left and the upper right. But they're putting that material in a position to succeed. So again, they've got our big roof overhang detail. And look at that photo on the second from the left and my sketch of it at the far left. So that's beautiful in so many ways. It's, in kind of a hot, sunny climate, it's essentially creating the sidewalk as part of the space, almost an extension of the house. It's an urban gesture to offer some relief from the rain and the sun by this house. And it's also protecting those walls built of this non-durable stone. And then they're also protecting these walls with a sacrificial layer of plaster. So the plaster gets beat up and falls apart, and that's easily reparable, and you maintain and you protect the stone that's really the load-bearing material that's taking the floor loads and the roof loads. And even Bernini, working for the Pope at the Vatican, did not have an unlimited budget. So you look at that beautiful forest of travertine columns that is colonnade at St. Peter's, and you go up and touch it, and it's all travertine, and everything you see is travertine. But up inside this arcade, you see some paint mock-ups here on the right. This was under restoration when I was there. You see the scaffold up on the left, and I got to go up on the scaffold and talk with them about what they were doing. So those lintels on the outside face are all real travertine, but once you get inside, those are actually all flat brick arches that are stuccoed and faux painted to look like travertine. So even Bernini, working for the Pope at St. Peter's, didn't have an unlimited budget, and he had to get away from the travertine where he could, and he put it in the right place both aesthetically and technically. He put it up high and sheltered, where you couldn't really tell from the ground that it wasn't real travertine and where it wasn't going to be exposed to the weather. The third principle is that the durability of an individual building component should be proportional to the consequences of failure, and I would add to the difficulty to inspect it, the difficulty to replace it if it fails, and the consequences of failure. So here's a kind of a very simple example. This is a door hinge from the natatorium at Foro Italico. So this is an early modern building, and it has a couple different dissimilar metals going on here. They have bronze and they have plated steel, and they're in a pool. So a very humid, high chloride environment, and you can see you've got corrosion going on here. But even if that fails, that hinge fails, it's easy to see it, it's easy to inspect it, it's easy to replace it if it fails. And if it does, the door drops the 1/4 of an inch to the floor and no one gets hurt. So in my mind, that's totally fine. On the left, you see another corroded door hinge, and this was from a very rustic kind of wood shop in a villa at a farm. And again, same thing, it's pretty corroded, but it was easy to see, easy to inspect, easy to replace, so no one got hurt if it failed. But you get into construction like this in the Imperial Roman Forum at the upper right. And so, you've got tons of stone connecting to tons of other stone. If you had corroding iron in there, cracking and spalling the stone, you could have a catastrophic failure, chunks of stone coming down from 60, 70 foot height. You could have a structural collapse. So even in those areas, though no one never saw it, you would find bronze dowels. So if you look around on the ground in the Forum and in other ruins in ancient Rome, you will see these bronze dowels sticking out of connections of columns to architraves and lintels, etc. So it's a precious material. They didn't put it where everyone would see it. They put it where they really needed it because they needed a durable material that would not corrode, kind of holding those pin stone-to-stone connections together. Bronze strap on the far right. And I would note that this idea that you put that precious expensive, durable material where no one sees it, this tends to conflict with the typical approach of value engineering, because what often happens in value engineering is the person doing the value engineering thinks it's their job to go in and take money out of the project where no one will see it. And what I'm saying is often you need to spend the money in the places you don't see, because those are the hardest places to get to, hardest places to inspect, and the hardest places to replace something if it fails. You're much better off putting the less expensive material where it's easier to replace later. So just kind of a compare and contrast on this. That's my little 1,300 square foot bungalow on the left that I'm sitting in right now. I can tell it was a very modest house when it was built, because most of the other houses in our town here, they might have pine on the second floor where no one sees it, pine floors, pine window trims. And then down on the first floor, if they were a bigger budget house, they had oak or maple or a nicer, or maybe some walnut. They had a nicer wood. So this entire house, everything is pine. First floor, the window trim, the floors, the windows, everything is pine. So it was not a big budget house. But a few years ago, when we did some work and we did some reshingling, we found that the sheathing was in great shape. Every window had a metal flashing at the head. So all the concealed details had held up really well, and we never had problems with leakage or durability. I would contrast that now with kind of an attitude toward McMansions, where the part beneath the surface is really cheaped out. The sheathing just keeps getting cheaper and cheaper, and all the money gets put into what the people see, like the kitchen counters or the high-end appliances. So it's a whole different idea of designing for durability than you often see with spec or developer construction. And the last principle is to recognize inherent vulnerabilities in the design while they're still on paper, and then design to minimize your exposure and susceptibility to them. So any design, even the best design, is going to have some Achilles heel, some weak link. So look very carefully for those, and then do everything you can to minimize your vulnerability to them. So an example of that I would give is Luigi Moretti's Gilles in Trastevere from 1933. So this is a pretty significant early modern building, this beautiful staircase you see on the right. And this was essentially like a YMCA of its day. In the early 20th century, a gymnasium for youth. So one of the things he wanted to do here in this gym was to have skylit surfaces from above. And he had a new material. He had this glass block, a relatively new material to create these skylights out of. So what Moretti did here, he realized the vulnerability of that if he put it right on the main roof surface. It's hard to make glass block cast into concrete totally watertight. It's still hard to do that today. So what he did, as you see on the right, is he raised each of these skylights over the gym up off the main level of the roof. So instead of having rain kind of sheet flow over this Achilles heel, all the sheet flow and all the rainwash is down away from them. And all that ever really hits these is what strikes it directly on the fly. And then he's also sloped the top of each of these little mushrooms slightly to get that water off as quickly as possible. So today, this is still doing well. And I went into this gym and it really looked great. I didn't see any leakage or staining at the skylight. On the other hand, a different building right across Rome by his rival, Del Debbio, he had the same idea. He wanted glass block skylights, and he put them right on the main roof surface. So there you see one at the upper left, kind of covered with mold. They're just constantly kind of dealing with pain and leakage at these. And on the lower right, you can see what they've done to try to mitigate it is they've just kind of given up and covered all of those with this translucent fiberglass, corrugated fiberglass, to just try to keep as much rain off it as they can, because they just can't really make them watertight. So two different approaches. Moretti recognized that vulnerability while it was still on paper and designed something to deal with it. Del Debbio did not. And I would say the corollary to that is that just accept that weathering and some amount of material degradation are inevitable, and make sure you design in a plan B to avoid a catastrophic failure when that happens. So on the left is, this is a close-up of an H.H. Richardson design building built by Norcross Brothers, really good contractor in the late 1800s here in New England, and a Tuscan village on the right. So you can see a very sophisticated American builder in the late 1800s, and Tuscan farmers in medieval ages and beyond had the same idea. They understood that you have large stones and you're building a load-bearing wall out of them. And rather than just have the kind of gaps that are irregular and get narrow at some point but really widen out, rather than have those be all mortar, because mortar will erode and degrade over time, especially in old traditional lime mortar, they've put in this sometimes called chinking, a lot of different terms for this in different regions and countries, but essentially kind of hammered these chunks of stone or brick into those spaces. And to me as an engineer, what this provides is, even when the mortar erodes or degrades, you've still got point-to-point contact between all these stones, and it makes the wall reparable. Now, if you didn't have that, and all those things that you see that are brick or small stones were just mortar, the mortar starts to erode and big things shift around, walls start bulging, walls start cracking. It's just not as durable or reparable really over time. And so what the chinking really does, it creates an alternate load path point to point through the stones, even when the mortar's eroded. And we've kind of seen that time and time again in different buildings. It can be the thing that really makes those buildings do or die over time as mortar does inevitably erode. So this building this is an H.H. Richardson building, tower in Springfield, Massachusetts, 120 feet above the main entrance. And there was essentially nothing left of the mortar when I got up there on that orange lift and started to look at it. But they had shimmed every stone, even though in this case they were ashlar, rectangular blocks rather than irregular rubble fieldstone. And that's really what saved that. Anything from falling or collapsing despite the loss of the mortar. And you see this also in arches. So if you think about traditional arches, you have a wedge-shaped stone and a very narrow joint, and the mortar washes out. The wedge shape, as in my diagram on the left, might shift or drop with the loss of the mortar, but it locks into a new position of stability and it avoids catastrophic failure. So the photo at the lower left is actually the bridge at Palazzo Farnese that's attributed to Michelangelo. And you can see the mortar's washed out. That wedge-shaped stone has dropped a little bit, and then it's locked in because of the wedge shape, and it hasn't gone any farther. So you do not have a catastrophic failure. This building at the right is a building in Boston that had very wide joints, and the brick was not wedge-shaped cut. So when that mortar eroded, the brick just dropped out, and a contractor put in those 2-bys just to avoid a further collapse or failure. So to wrap up, I'd like to go back to Vitruvius and have him provide some closing thoughts. So in book 1, Vitruvius told us what qualities a building must have to be considered architecture. So he set the bar quite high. And famously, he told us that all buildings, whether they're public or private, whether they're residential or civic or utilitarian, they must have 3 qualities to be architecture. Not to be great architecture, just to be architecture, they must have these 3 qualities. And of course, those are firmitatis, which he names first, which is durability, strength, soundness; utilitatis, which is usefulness and functionality; and venustatis, which is beauty. So he set the bar quite high for what it takes to make architecture today. And I think it's up to us to try to live up to it. So thanks to all who allowed me to do the research a dozen or so years ago, the American Academy in Rome, the National Endowment for the Arts that funded my fellowship at the American Academy, and Simpson, Gumperson, Hager, who were great in giving me a year sabbatical and healthcare while I went and did this, and so many Italian colleagues who literally opened doors for me and let me up on their scaffolding. And here's just a list of some of the people who were just a huge help to me, opening doors for me the year I was in Rome. And with that, I would just love to take your questions. And I also have a handout that summarizes these principles of durability, so you don't have to scribble them down. So I'll find a way to get that to David and Sarah so that anyone who wants that can get a copy of that. It's just a PDF we can email around.
Matthew, again, thank you so much. I mean, this is just so thought-provoking. I share your lecture with so many people through the years. It makes you really look at architecture so differently, in a way, style blind. And it goes back to one of your earliest comments you talked about in the beginning, which is the importance of resilience. I think if the world could put a priority on resilience over design, our entire architecture could be viewed differently in all different regions. So in any case, thank you so much. My first question is from me. I have a question about the pins in the columns to the beams. What was the actual purpose of that? It would seem that the dead load of the beams would be enough to keep things secure compared to the actual strength of that pin, or was it for earthquakes and tremors and moving over time? Is that little pin was enough to hold it together?
That's a really great question there. I'm actually going to go back to that. So one thing that's not super well known about Roman architecture is when you look at these kind of massive structures, they were typically built stone on stone with these bronze pins and dowels in between. So the way we would typically build a massive masonry structure here in the States in the 1800s, of course, it's all just mortar and it's kind of buttered up and laid up on mortar. So you're relying pretty heavily on the mortar. So here, actually, if you look at the far left, you see that little channel coming out of the hole for the dowel. So in this case, there's a square hole there, and then there's a little channel coming out. So the Roman Colosseum is another example of this, Bondigar. So essentially the bronze dowels would be driven in very tight into a hole drilled in the marble on one surface. And then on the other, they would put it in and actually fill that with molten lead. And so that channel was a relief channel that allowed them to totally fill that with lead. And then it was a dowel-to-dowel connection, and the excess lead could come out through those little channels. And so all the kind of pock marks that you see in the Roman Colosseum, I know U.S. soldiers got there and thought the Colosseum got shelled, and Italians had to tell them, no, it's been like that forever. So what those really were when so many Roman buildings became essentially quarries or places to just grab materials in the Middle Ages, the little drips of lead on the surface that came out through all these channels essentially told anyone who wanted to go and steal lead and bronze where to go. You just follow the lead, and it led to a bronze dowel, and then they could get some money for the bronze dowels or use them themselves. So a lot of bronze got chiseled out and pocketed out of the Colosseum with this little telltale of the lead leading to exactly where it was. So that's how they put them together. So there was actually very little reliance on mortar. Essentially, you had the friction. You're right. In a true gravity load situation, just pure gravity, the weight of the stones is enough. But of course, the central Italian peninsula is a highly active seismic zone, and there have been a lot of earthquakes there through the years. The earthquake a few years ago in L'Aquila was an example of just how devastating that can be. So I think one thing that these added in terms of seismic is not only just the kind of shear resistance you get from having a dowel lock two materials together, but I think the ductility of the bronze and the lead added even yet another layer. So it's almost like you've got a little bit of attenuation in that seismic joint. So it's both holding it together. It's not going to let it shift, but it's also got just a little bit of give to it, which probably helped attenuate some of the seismic events as they started to shake these big masonry structures. So obviously it's worked really well because the Colosseum's still standing. And
I mean, that goes to your point of Darwinism. They had to figure that out at some point.
Right.
What? We've had a bad earthquake and we're seeing movement. We got to put these pins in. It was modern once. It was a modern design concept.
Exactly. I mean, I would much rather be in an ancient Roman building built with bronze dowels than in a Renaissance building where they just laid up everything with mortar. If there were an earthquake, that's where I run.
So by the way, if anybody has any questions, please, there's a Q&A button in the middle bottom of your screen. Jump on and ask a question. One question is asked is for the embedded stringing courses that you were explaining. They're pitched as they go from the inside to the outside of the walls to shed water. But they're also they're a bearing plane. And does that cause the masonry to sort of slip to the outside? Why doesn't this occur?
Yeah, so it's a good question. It's just a very slight wash slope. And the other thing you sometimes see is if the stone is cut with just a little bit of a raise on the kind of the back edge, then it's almost a dam that can force water off when it's, when it gets to a little bit of a height. So it wouldn't be a dramatic slope because I agree that would kind of create like a slip plane where the masonry could slip and slide. I should add some photos of that. There's a beautiful book of Italian construction that actually shows like some sections cut through there that I should go back and pull some graphics from. And I've seen similar things actually here in the United States in 19th century buildings. There was a building in Louisville, Kentucky that I went to look at that for a project where, essentially these buildings had been abandoned for 20, 30 years, and a building had collapsed, a row house, and it was the row house next to it. But in the manner the older building next to it had collapsed, you could almost see like a pure section through a facade like I had drawn, and you could see how that band course actually went right back into the wall and was embedded, a couple feet in there, essentially almost the width of the wall.
Fascinating. Another question, which sort of goes back to what we were just talking about, can you say it again? It was resilience over aesthetics with a question mark. So that really, I think the question is that, are we really talking about technology / resilience over art style? And it's not about the details, it's about the resulting technology and invention of getting the water out. I think that's what the question is asking.
Yeah, I guess resilience over aesthetics. So, I guess seeing that these technical details that were really important and worked really well transcend different styles, that you see them in ancient Roman, and then you see them in medieval, and you see them in Renaissance, you see them in Baroque, you see them in Rococo. I would almost say that it's a false dichotomy. It's not durability or resilience versus aesthetics. You can have both. You just have to understand what you really need to do for technical detailing, and then don't sacrifice that for the aesthetics. Right, so a window can still be detailed like a Renaissance window, or a Baroque or a Rococo, but you've got the critical, essential technical details in there to make it work, and you don't go beyond that. Like Gropius went beyond that, right? He probably could have done a slightly more streamlined version that had all the technical benefits of the older kind of farmhouse window detailing, but he went too far, and he had a really bad detail that almost funneled water into the wall through the sill.
And as you mentioned, a lot of these technologies relate to vernacular, correct?
Yeah, and I think the vernacular is a great point to make with this discussion, because the vernacular, I think, is so insulated from stylistic, from the stylistic flavor of the moment, that it is much more focused on kind of that fundamentally sound way of building, right? So, you look at those Tuscan hill towns. I had that example of the chink stone, right? There isn't a whole lot that changes in those Tuscan villages or hill towns over hundreds and hundreds of years, right? The vernacular remains the vernacular, because they're not changing every little detail every time, something changes from, stylistically. Oh, we need a swag now. We need this now. We need that now. They're very simple, and they're focused on what works and what's simple and what's honest and what's local and what they have available. And those things just don't change much over time.
In the picture that you showed of the small flat roofs, and you talked about the vulnerability of the water on those flat surfaces to get into the house, the first thing I thought of was, as bad as that is in southern environments, up here with ice damming and freezing and thawing, it just multiplies that problem by multiples, I would think.
It does, yeah. I think the flat roofs and the inverted step pyramid and the roof overhang all make the point that the overall form has a lot to do with durability. I think a lot of people, if they haven't really looked at it closely, they might think durability is about the material, right? It's like the Three Pigs houses. There's straw, and then there's wood, and then there's brick, and then there's stone. And I can't afford stone. I've got wood, right? But at least I'm not straw, right? And really, what those examples show us, and in particular, those kind of Tudor and Elizabethan houses, and even the Tufo Giallo, is you can take a pretty lousy material that's just, it wouldn't be durable if you left it out in the rain by itself, just sitting in the yard, right? That wattle and daub would turn to oatmeal real fast. But you put it in a very clever orientation, and you protect it well. And the same thing with the Tudor, and you can make it last for centuries, right? So the form is really important. So maybe part of it is we should start thinking about the form first in terms of durability, sustainability, resiliency, and not let the form be some kind of whimsical thing that's just the creation of, I don't know, chipboard or museum board, or today, like some sort of BIM model, right? It's not a still life. I mean, we have to think about it in terms of how does it manage water.
The Three Little Pigs is a great analogy. If you think about cheap commercial construction versus maybe a low budget state school college campus versus an Ivy League campus, and the way that they view a structure to live 20 years versus 50 years versus 125 years. And the fact that they cost twice as much, but it's going to last 5 times as long. It's just a very, again, resilience is a really important thing to bring back into the dialogue, I think.
Mm-hmm.
So great question here. I seem to recall there was an effort in New York City to remove projections before they fell. I wonder if this led to increased deterioration of the walls below.
Yeah, New York had Local Law 10 in the early 1980s, and that was really one of the first, I think it was the first facade inspection ordinance in the United States. And today, a lot of cities, Chicago, Boston, San Francisco recently enacted one, have ordinances that facades have to be inspected every so often, and now there's even an ASTM standard for that. So that happened sadly in New York when a Barnard College student was killed when something fell off a facade. It was a chunk of cast stone or early 20th century concrete that fell and struck her in the head and killed her in the early 1980s. So as a result of that, early on, some owners were just ripping cornices and overhangs off of buildings rather than trying to repair them, because they saw that as the cheaper option. And if there were a lot of cracks or damage to it, that's what they were doing. There are some cases where not only is the cornice important for, the overall durability of the building and keeping water off the walls and all, but there are some cases where the cornice there's like a counterweight of a parapet on top of a cornice. So, I mean, structural engineers in New York started realizing you have to be really careful what you take off, because sometimes it's holding something else in place or pinning something else in place by its weight. So sometimes those big cornice overhangs actually worked because they had a parapet on top of them to help keep them from overturning. So cornices are something you need to look at very carefully.
That's fascinating. This is a comment. I think it was common in the earliest 20th century to have cornice blocks span the entire wall. Effectively, the cornice was a continuous stone flashing. Cass Gilbert detailed this way in Waterbury's City Hall. I suspect it was typical when you could afford the large stone blocks.
So you're saying they're saying a single large stone for the cornice?
I think they're saying one large stone block.
Yeah, I guess I've seen them both ways, where it's one, sometimes where it's one very large stone block, sometimes where it's essentially a series of corbels built out. Yeah, one of the trickier things too is when you get to a corner. So if you can imagine, you can draw something that would work in section, right? And you have a stone that comes back and it might get strapped down, or it might have some weight on it to help it come out. And then as you get to a corner, you've actually got a projection that's going 2 ways, and you don't have that much that's hanging back. So Formelli is that the Italian textbook that I mentioned. I think University of Notre Dame has copies online, where he just drew these incredible details of how these buildings were actually built. And you can access it online via their digital library. And maybe I can pull a couple of those details and send them to and share them. But he's got some real beautiful, like, cutaway isometric drawings with watercolor, kind of showing how some of those cornices are built and how some of the band courses project back into the walls, and how to detail the corner where you come around and there's actually, there's more overhang and there's less support as that cornice stone turns the corner.
I'm curious, you've been in this field for so long, what your thoughts are on modern or traditional architects that you think are actually making an effort to push the envelope while still respecting details, and where you might see something and go, wow, that's not something I would have seen before, but they're actually paying attention to the things that are important to me, being you.
Yeah, so one architecture firm, I've never met them, but I've admired their work and the magazines and all, and I actually wrote an article several years ago talking about designing for winter and, you know, designing for snowy climates and all of that. And they're doing beautiful modern work, but they're embodying a lot of those principles. Is Macaulay and Sweet Apple up in Nova Scotia. And so they have some buildings with just very large roof overhangs, and one where, you know, kind of the roof almost wraps around the building. I thought of it as almost like the fisherman's hat, you know, the classic yellow hat with the flaps down, and they're building these buildings on, you know, on the coast in Nova Scotia where the storms blow in off the sea and just really rough weather places. And so it seems like they've brought a lot of how to deal with that climate into the overall form and aesthetic of the building, and really just pulling it off beautifully aesthetically as well.
For one, from me, and I don't know if it's much about the technology of the overhangs, but Ike Kligerman Barclay is, at least they're on this effort of trying to use some mostly proven shingle style technologies and really trying to interpret them. And it always amazes me to see the different interpretations that they come up with. SMACNA issued a reprint of their 1929 that has some great details.
Yeah, so the SMACNA manual, which is the sheet metal, I'm going to get that wrong, but it's Sheet Metal Something Contractors Association. They have a beautiful handbook, and we have a few old copies floating around the office. I used to borrow Werner Gumpert's really old copy all the time because some of those old details are just better than the new details, showing exactly how you form all the hems and all the locks in sheet metal work. And another great one that you can still buy online from Revere is Copper and Common Sense. So Copper and Common Sense, a lot of the same details, hems, you know, standing seams, flat seams, locks, double locks, how to put, you know, valleys together, everything like that. And they're kind of focusing on copper. SMACNA was a little more general and also applicable to other metals. And some of them are the same, but sometimes when you get into other metals, obviously copper solders beautifully and some other metals don't. So sometimes you're a little more limited with what you can do with aluminum than copper. But they're both great handbooks.
Well, Matthew, again, you hit an absolute home run. The majority of everybody that started is still here, which is quite a testament to you and the importance of what you're talking about. Thank you very much for saying yes to us. This has been great.
Happy to do it. Thanks so much for joining me this evening.
Thank you. Bye-bye, everybody.